Alrighty, y'all. Today we're taking a look at question 7 for homework 5. And for this one, we're trying to find the induced EMF per unit length of a solenoid, cylindrical solenoid. Again, still don't know how that's pronounced, but that's fine. Right, so we have that we're given 150 turns per centimeter, right? So since it's turns or loops per unit length, we're going to use the lowercase n, right? So that's our 150 turns per centimeter. Again, base units, always base units. That's going to be 15,000 per meter, right? We're given a radius. Our radius is 1.7 centimeters. Again, base units, always base units, 0.017 meters, right? So we're given our rate of change of the current, our di dt, which is 6 amps per second, already in base units. Lovely, don't have to do anything with it. Right? So we're going to start with our equation for our magnetic field, right? Because we're changing a lot of stuff. We're trying to find the EMF. We're going to need the flux. We're going to need the magnetic field, right? So magnetic field for a solenoid is mu naught n times I. But we don't have our I. We have our di dt. So all I'm going to do is I'm going to differentiate both sides of the equation with respect to t. That gives us dB dt equals mu naught, doesn't change with time, n isn't changing with time, but I is. So we get di dt. Cool. Now we can just plug in here. Our mu naught is 4 pi times 10 to the negative 7. Our n is, what we said before, 15,000. And our di dt is 6. Multiply that out. That gets us our, I did not mean to erase that, dB dt. Right? So we're trying to find the EMF induced per unit length. So our EMF induced for a solenoid is our, right, that's our EMF induced for a solenoid. That's our capital N. I can't write today. Flux dt, right? It's going to be our magnetic flux differentiated with respect to time times the number of loops in the section we're talking about, right? So this capital N, our number of loops, all that is our little n, right? Which is loops per time times the length that we're looking at, right? Because this is going to be number of loops per length is going to give us our little L, and we multiply around, whole deal, whatever, right? We get it. So if we divide both sides by L, right, that's going to give us our EMF per unit length, and now we get to use n, little n, in there. Okay, so that's like a double win-win, because this is what we're solving for, and we already have this one. Lovely time, right? So now we just have to get our change in flux with respect to time, right? Since our magnetic field isn't changing over the area we're looking at, we get to use our equation that our flux, magnetic flux, is BA cosine theta, right? The area vector for a solenoid is like kind of like the cross section here coming out here. Our magnetic field is going in the same direction, right? So our cosine of our area and between our area and our magnetic field vectors is going to be 0. Cosine of 0 is 1, which means we get to ignore that lovely times. Magnetic flux is just B times A. But now we don't have B, we don't have our magnetic field, we have our change in magnetic field with respect to time. And we're not looking for our magnetic flux, we're looking for our change in magnetic flux with respect to time. So I'm going to differentiate, again, I'm going to differentiate both sides of the equation with respect to t, right? So d flux dt is dB dt, right? Because that's changing with respect to time, times our area, because our area doesn't change over time. It's always going to be the same, right? So now we can plug in all this jazz, because we already solved for dB dt before. We have a number for it from this. In our area, we can just get the cross-sectional area of the solenoid with the radius, right? So our area of this circle is going to equal pi r squared. Our radius was 0.017. Again, meters, because always base units. And we square the radius, right? Pi r squared. So now all we do is we combine all of this. So we get our EMF per unit length is going to be our N, which we have up here with the 1500, right? We're using that N here. 15,000 times what we just calculated, or what we're just putting together for our deflux dt, right? So that's going to be our dB dt, which we're going to pull from up here. So I don't feel like rewriting this, so I'm just going to, right? That, oh, it's encroaching on the other thing now, right? So that's going to be the first part of our magnetic flux times our area, which we just did over here. Right? So we have, from our original equation, our N times our magnetic flux, which is just all of that, because we got that from here. And if you calculate all this out, if you punch all this into your calculator, it will give you your answer of electromagnetic field in volts per meter, because again, our electromagnetic field is in volts, length is meters, because these are both base units, always base units, and you don't have to worry about anything at the end. Yes, this is just going to give you your final answer for electromagnetic field per length of the solenoid. All right, well, I hope you found this video at least a little bit helpful. Let me know if you have any more questions about this problem or any other problem that you want me to explain, and I will do my best to try to explain it, because I guess Sydney explains stuff.